Okay, great. So welcome back after the coffee break. For anyone who's wondering, we're running late, but yet we're running 10 minutes ahead at least of the printed schedule because one talk was canceled, and now it's our pleasure to hear József Fortágh. What's that? Oh, it was moved up to yesterday, like Henry Kleiman thought yesterday. Yeah. Please be.
Thank you very much, and hello everyone. It's very nice to participate in this conference. So, thank you for the invitation and being here. I will be reporting about our work on atoms on superconducting cavities, coplanar cavities. There is very much related work here in the group of our host, Stephen, also in the group of Fabricated, Zurich, also Safwan has related work, and I see in the audience Michel Brun, all these groups contribute to this field. Today, I focus on the findings that we make in our group. I work with a couple of PhD students. I have colleagues, senior colleagues who are in the discussion circle, and from the solid state side, I have a colleague Rydberg who is supporting us with microwave cavities. So the next slide.
Might have to click on your presentation. Yeah.
Let's see. Yes, this is the physical system that we look at in our experiments. So what we see here is an atomic cloud that is trapped in a magnetic trap close to the surface of a superconducting coplanar microwave cavity. In this presentation, I look at a single atomic cloud interacting with the field of a driven microwave cavity. So the system is interesting because cavity, a microwave cavity, is in principle able to mediate interactions, long-distance interactions between atoms that are at different antinodes of the microwave. Different to systems where Rydberg atoms are next to each other, the cavity is mediating not only next neighboring interactions, but all interactions. That is giving an interesting perspective to look at interacting spin systems. And there are a couple of proposals by Rabi-oscillation, who is discussing that even microwave cavities with thermal photons will allow us to perform gate operations. So this physical system we implement in two different experimental machines. One is a cold atom setup with a 4 Kelvin helium flow cryostat, and the other is a helium 3 helium 4 dilution refrigerator that is reaching 15 millikelvin temperature, but it's so difficult to operate that none of my people like it. So all the experimental data that I'm showing is on the 4 Kelvin system. Now into the lab. I think I have to step here the pointer, or I cannot change the slides with this device. So the look into the lab, we have a vacuum chamber in which we included electromagnets for atom trapping and the helium-4 cryostat. Now, if we look into the vacuum chamber through this window, then we can follow the experimental cycle. First, we prepare a magneto-optical trap. This is rubidium. Once the atoms are in the trap, we trap them magnetically, compress them in tightly confining traps, cool evaporatively, and pick up the atomic cloud with an optical tweezers that is moved to below the cold surface of the cryostat. So those electromagnets in the vacuum are at room temperature. Here we have a 4 Kelvin cryostat with some cryo-shielding. And here below the chip, we take absorption images of the atomic cloud, and in this cryoshield we installed an ion detector, a channel with some ion optics that allows us to detect individual ions. Essentially, it's important for the Rydberg experiment, the field ionization, we detect the ions by counting them. Now, at the cold surface, we operate a superconducting chip. On this picture, we can see the sapphire substrate with niobium biocomponents. Some of them are microwave cavities and other biocomponents for magnetic trapping. I will show you another picture about that. Now, what we see is an atomic cloud, which is trapped down to tens of microns to the chip surface. Typically, we move the atomic cloud between from 150 micron far distance to down to 20 micron close distance to the chip surface. These are typically 10 to 100,000 atoms at typically 500 nanokelvin temperature. In the system, here the biocomponents would be at the surface. We measure control interaction between the atoms, and the goal is to couple atomic states, hyperfine states or Rydberg states to the field of the microwave cavity. We work with rubidium atoms, rubidium-87, and we trap them in the lower hyperfine ground state magnetically. We use harmonic magnetic traps, thermal atoms, or Bose-Einstein condensates. The hyperfine transition of the atomic cloud of the rubidium atom, 6.8 gigahertz, was important to us when fabricating the cavity. The first goal of the experiment was to couple the hyperfine ground states via a superconducting coplanar cavity. Therefore, my colleagues in the solid state department fabricated a coplanar cavity, which is consisted of a center conductor and ground planes around niobium on sapphire substrate. When we characterized the first results, we found cavities with 6.8 gigahertz resonance frequency, quality factor around 10 to the 4 at 4 Kelvin. Higher modes have a lower quality factor, which will be also important in this presentation, and the chip has integrated traps. We see that the resonance frequency is tunable with the temperature, so within a practical range, we tune the resonance of the cavity a few tens of megahertz, and this is a knob that we can adjust to the atomic frequency. Now, the first experiment I'm describing is with 100,000 atoms at about 20 micron above the chip surface. Here, the cross-section of the coplanar microwave cavity in the center, the center conductor, and to the two sides of the ground plates. The atomic cloud, the extension of the atomic cloud is illustrated by these lines. First, we apply microwave pulses of variable length, bridging the lower and upper hyperfine state of rubidium. It's a single photon, therefore we couple the 1 minus 1 state to the 2 0 state. They do experience differential Zeeman shift in the trap, and first we are not surprised that the Rabi-oscillation is dephasing on a short time. The atomic cloud is extended, the magnetic trap, and the two states, the two hyperfine states, do have different Zeeman energy in this field. Therefore, we can think of a coupling, which is two-photon coupling, coupling two states which do have the same first order Zeeman shift and are both trapped in the trap. We take the cavity photon plus with an external antenna a radio frequency photon and couple the two states, where we again observe a Rabi-oscillation. Of course, this is a two-photon transition and a much lower Rabi frequency. You watch the time scale, but the same finding that the oscillation is dephasing just after one oscillation period. Now, the question is, why is that? And you see already theory curves. Now, the red is the fitting of the data, and the black line is a model which considers the inhomogeneity of the microwave field close to the coplanar cavity. So what is illustrated in this picture is the coupling strengths, the single photon coupling, single photon, single atom coupling, which is strongly inhomogeneous. So essentially, we have eliminated the differential Zeeman shift of the first pair of hyperfine states, taking the two-photon transition. What we didn't eliminate, the dephasing due to the inhomogeneity of the driving field. So at the same time, if you look at this color bar, then you find the tiny number for the single atom, single photon coupling, which is not a measure but a calculated value, which is less than a hertz where the atoms are. And this is certainly a nice physics to look at, but the question, what is it good for? It's a super weak coupling. We can't use it. Now, how to increase this coupling? One option is not to take a single atom, but to take many atoms. Instead of a single atom, we could take 1,000,000, which is possible to prepare. That we would enhance with the square root of n. Yeah? That means we fill this circle with many atoms and coupled to the cavity. However, the inhomogeneity of the driving field will still limit our coherence. This is a step that we make now towards Rydberg atoms. So instead of taking many ground state atoms and using the collective enhancement, we could take a single Rydberg atom, which with an strong electric dipole coupling may bring the same Rabi frequency. So we changed our experimental system, we expanded it by a pair of lasers, which is exciting a Rydberg state by a two-photon transition. The Rydberg state will be around 48, 47, because we find in the state pair a transition between Rydberg state R1 and R2, which is matching the third harmonics 20.55 gigahertz of our cavity that we have already in place. So this is 3 times 6.8 gigahertz. Here you can see now the detector. It's a channeltron with some extraction electrode for field ionizing single Rydberg atoms and counting them with about 50% efficiency. Now, closer look to our chip. Here we have the coplanar waveguide cavity. We have a Z-shaped wire for trapping. We apply some homogeneous field from the side, and at the end, the atomic cloud is in a magnetic trap that consists of these applied fields plus some persistence currents that we induce by applying those fields. In this case, we trap the atoms at an antinode of the electric field of the cavity, which is at a different place than the magnetic field antinode of the cavity for the experiments before, and drive the cavity. Now, if we go with Rydberg atoms to the surface, then we immediately face a problem that many of us have investigated, is a stray electric field close to the chip surface that is results of add atoms sticking to the chip surface. Exactly those atoms that we use for the experiment may stick to the surface. They give the outermost electron into the surface, and we have dipoles. So the field is typically very inhomogeneous. Here in this cartoon, we see the shape of the cloud that is prepared above the chip surface, and atoms are deposited there. And there are many, many measurements that are even more than here listed, characterizing the field distribution and the impact on experiments. For example, impact on Rydberg atoms, which is a spatial variation of the star shifts of the Rydberg states. So depending on at which distance we prepare the Rydberg atoms, the state is shifted. So this has constraints on the optical excitation of Rydberg states, depending on the surface atom separation, we need different laser frequency to excite a particular Rydberg state, and it still has constraints on the coupling to the microwave. Look at the particular situation on our chip. I take the chip. This chip surface is now partially covered with rubidium. Now, please turn the whole diagram by 90 degrees. So to this left is the chip surface, and this electrode is here to the right. And on the diagram, we can see the electric field as a function of the distance to the surface. The dashed line is the straight field of adaptance. The black line is a field that is the sum of compensation field that we add by applying voltage to the grounded chip surface. And this extraction electrode, so it's a homogeneous field in the Z direction, we can lift up or down the stray electric field. However, what we cannot do in this setup is compensating the X and Y directions of the stray electric field, such that the field magnitude will have a non-zero value. Although we compensate the Z field completely, we end up with a stray electric field of a few volts per centimeter in the center of the chip. So the electric field at the minimum has a parabolic shape, which has the result that the Rydberg states that we excite are stark shifted. Depending on where I am, at which distance to the surface, the Rydberg state is in resonance with the laser beams, which have a given frequency or not. So in our situation, the atomic cloud has a large distribution. It is broad distribution. It's prepared now about 130 micron from the surface. This red line. The Rydberg lasers are illustrated by the blue. It should be at the center also blue, but what we illustrate is the gray is the excitation probability. The Rydberg state R1, which is our starting state, is excited here in the center of a trap, and the insert shows that the resonance is given for two different positions inside the trap, and therefore we do not excite the R1 state, the entire cloud, but in layers parallel to the surface, which are at the separation of, let's say, 110 and 120 micron. So you can imagine it in a way. Here is the chip surface. The stray electric field is making the stark shift, and because of our compensation, the electric field is first decreasing and increasing again. There will be two layers from the chip surface where the lasers are resonant, and in these two layers we excite Rydberg atoms. So this is a complicated situation. It would be easier if it would be one layer, but we can work with it. I note that besides the target state, which is R1, there are also other states in the Stark method around which we excite. So we have a mixture of Rydberg states from which we start coupling to the cavity. So the closer look, laser excitation, we excite the state close to the 48D transition. Here is in the magnetic field the Stark map of these states. The area to the left is the area which we cannot access because of the stray electric field at the surface. And here we can see that the resonance of our lasers is hit by the green and the yellow line, and the green line will be the R1 state that we look at. So to this state, we select state R2 at a separation of 20.55 gigahertz. This is in the manifold. This is in the 47 manifold. As you can see, there are many states that could be excited. And in this, we look at exactly those state pair which have a differential shift, exactly matching the cavity resonance. So we have a stray electric field at the chip of 3.4 volt per centimeter, and here in the circle, one of these bright blue lines is crossing exactly the cavity resonance. So this R2 state is the pair to the R1 that we can use. Yeah, depending on the electric field, or depending on the cavity frequency, we would be able to take another one. But the cavity frequency, we cannot change that much that we go to a state with a higher dipole moment. The selected state has 30 dBi. So if we would be able to tune the frequency, we would go here. If we would be able to tune the electric field in the X, Y direction, we would go to another state. Yes, this is something we learn for the future. For the moment, we find a state pair that is resonant with the cavity. So there we look at. The experimental sequence is the following. We excite the R1 Rydberg state within 1 microsecond. We employ the microwave pulse for a variable time, and then we employ field ionization. We ramp up voltage on the extraction electrodes to 135 volt within a microsecond, ionize the Rydberg atom and count it. So essentially, in a single experimental run, we repeat this cycle with 3 kilohertz repetition rate 300 times. So we gain a lot of data points without destroying the atomic cloud. And on average, 1 Rydberg atom is excited at one time. And now, as a function of the microwave pulse length, we look at how many atoms are in the R1 and how many atoms are in the R2 state, and would like to observe the oscillation. The discrimination is challenging. First of all, if the microwave is off, then we see that the 48 state, the R1 state, is arriving faster at the detector. And if we turn on the microwave, we see that the R2 state is arriving later. So we can define time intervals T1 and T2, in which we can be sure that in T2 only the R2 state is arriving, while the R1 state is, as you can see, it's a bit smeared out, but mainly arriving in T1. This scheme, we compare now the number of detected ions during T2 and T1 as the function of the microwave pulse length, and observe an oscillation which depends on the power of the microwave. What we see again is an oscillation which is strongly damped. And this is still the reason that the driving field of the cavity is inhomogeneous. Here, the experimental situation is a similar image than before for the magnetic trap. Here we have the atomic cloud. The optical excitation is in 1 or 2 layers. Actually, we should consider that the excitation is on the top and the upper side of this line. We excite in these 2 layers, and across this layer, here you can see the layer is parallel to the surface, and the electric field of the cavity is changing from left to the right, so there is still inhomogeneity. So what is our finding then in these experiments where we drive Rydberg transitions or magnetic hyperfine transitions on an atomic cloud? The inhomogeneity of a coplanar cavity is a problem. So there are certainly ways around. This is on the to-do list for the future, but this is the takeaway message that inhomogeneities impact these experiments. Now, we also saw that the star shifts of the Rydberg states is an issue. Therefore, we decided to look at the star map of rubidium that we use for those experiments in a completely separate system far away from the surface. So essentially, we create a magneto-optical trap. In this magneto-optical trap, we with 780 nanometer light always present, we excite with a blue laser that is focused to a light sheet, Rydberg atoms, again in a light sheet. And so the Rydberg atoms in this sheet are ionized and extracted, afterwards move to an ion optics, and we image to a multi-channel plate the position of the Rydberg excitation using a delay line, also the time. So essentially, this is an imaging of the Rydberg excitation in a given sheet. What we can learn with this. So essentially, if we vary the frequency of the Rydberg excitation laser, then we can excite different Rydberg states. If we vary the applied voltage, we can excite various Stark states. So what we can do in the experiment is taking a Stark map. It's probably hardly visible, but you can probably see. Can you see here the Stark lines are wiggling? We vary the laser frequency and the extractor voltage, and we can map the Stark map. Since it is in a mode, it's a continuous measurement. This measurement is taken in a very short time. We can go from low fields to to very strong fields with broad lines due to ionization. We can go back. There are some areas already at high fields where we can still see narrow lines, and we can look at that more carefully. We use these measurements up to check and calibrate our theoretical model based on complex absorbing potentials as the measured and the calculated diagram. I do not overlap, but you can pick details that is overlapping for low and high fields. And now we can use the numerical code to look at interesting state pairs, R1 and R2, that are interesting for coupling to a cavity, not only at low fields, but at high electric fields. So that's something which is around the classical ionization limit. These fields already, we consider that the Rydberg atom is ionized at, classically ionized at this field, but is not. We still see narrow lines that can be excited from the ground state. So the excitation probability is color-coded here for polarization. And we can calculate the ionization rate. So there are some states that can be excited. So the diagram is the same. Here is the excitation probability, and here is the ionization rate. Look at, for example, this point. This is a strong probability for exciting, and the state is not ionizing. Look at this point at the red. This is a strongly ionizing state here, but it can be still excited. And now I pick this area and say I overlap the two diagrams and say that, look, we can excite Rydberg atoms, for example, here at the Stark map, or here, and those two Rydberg states have a different dipole moment. The dipole moment is essentially the gradient of the Stark map with respect to the electric field. So at the point A, we have a strong dipole. At the point B, we have a weak dipole at high fields. And the state is long-living, it's not ionizing, so we can work with that. On the other hand, for the detection, we would like to ionize the state. We can change the electric field just by 1 volts per centimeter. It's a tiny change. We don't need to ramp up the field from 0 to 130 volts. We change the field depending on the geometry just by a fraction of a volt. And from a stable state, we end up in a strongly ionizing state. For this, I look at an experiment in which we excite the Rydberg state in a gas, in a mode. For a given field, for example, for A, and then ionize it by increasing the electric field just by a volt. volt per centimeter, or for a different strength, and then look at the Rydberg blockade, dipole blockade. Essentially, strong interactions mean a large dipole blockade, weak interaction, weak dipole blockade. And if we use this ion microscope, as I've shown you before, and image the positions of the ions resulting from the Rydberg atoms arriving at the multi-channel plate, we can form the two-dimensional correlation function of Rydberg excitation. We see the strong dipole giving the strong blockade, weak dipole, a weak blockade. So at the same time, in these dark maps, we saw lines. Maybe I step back for a moment. Here we see lines with strong dipole, weaker dipole, negligible dipole, and we find also state pairs with different differential shift. So the these diagrams I find interesting in finding state pairs with negligible differential shift. For example, for the purpose of coupling to the cavity, which is certainly an interesting thing to look at, besides of dressing Rydberg states to eliminate the differential shift. So essentially, this may be an interesting component for the experiments also on the chip. At the same time, if I bring the two subjects that I discussed today together, the control of dipole interactions at high electric fields and the control of Rydberg atoms on a chip, there may be an interesting opportunity that the Rydberg atoms that interact via the cavity on long distance, they get an additional next neighbor controllable interaction by slightly changing the electric field. And the fact that at high fields, the ionization can be switched off fast, it is an interesting opportunity. At chip surfaces, we do have always electric fields. So far, we focused on reducing those electric fields. That's a strategy. And with microwave testing, certainly we will be able to identify, and there are also results already on states which have negligible differential shift. At high fields, the same may be possible, that we may look at in the future. With this, I would like to conclude this presentation. Thank you much.
Yeah. So in the regions of your tracker, you have inhomogeneous electric field. You will accelerate or decelerate the start states you prepare, depending on whether they are low field or high field. Do you see such effects?
The experiments on that are on a very short time scale. Therefore, we don't see on the microsecond time scale, but the dephasing may be exactly from that. So essentially, I believe that this is, we didn't put it to the calculation, but the model was not exactly fitting the curve. The acceleration may be an issue. Now, the question is what happens with those states. Yeah. With such state pairs. Yeah. It would be an interesting thing to look at. Huh?
Thank you.
Yeah, sure.
Yeah, question about the future. So some of the bigger fathers here are even like the large dipole build on the chip itself, and then the field in homogeneity. I was just curious on those two things. Do you have plans how to fix those in the future, or make them better, please?
Yes. So we do now experiments actually in Paris. The group of Michel Brun looked at if they cover the surface with rubidium, the anode that they work with, then these charges are eliminated. So that's an interesting strategy, and My question is at this point whether or not this layer would change the superconducting cavity's resonance. So, and I may be able to answer this question now, but we are just doing these measurements. Yeah. Yeah.
And also the field modulating, or curious.
So essentially, the absorbed fields, if the chip is covered, then it may be solved. But the field inhomogeneity, how the electric or magnetic field of the cavity, this coplanar cavity is decaying, is not changed. So this is an issue that remains. So either we consider that and we can use that, or we need a different geometry to get to a useful system. Yeah.
So in these very strong fields where you can switch a little bit to switch between interactions and non-interactions, are those switching fields compatible with the inhomogeneity of the field?
Less.
Less appearing.
Yes.
Like okay to.
Yes. So this is okay. If you ask here if essentially some part of the atomic cloud is in one or the other state. Yeah. So since we excite all that, okay, here is the chip surface, something which is healthy. We excite in a thin layer. Yeah. So not across the atomic cloud. So we have to distinguish how large is the atomic cloud, or how much is the extension of the active atomic cloud that is in the Rydberg. And this is again much smaller. So we excite in a layer of 300 nanometers. Yeah. By the cloud can be several tens of microns, depending on how we prepare. So, but it's an interesting point. Yes. Yeah.
So it's the inhomogeneity across this tiny region that makes the
yes. 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 At the same time, it is a sheet parallel to the chip surface. So not only these 300 nanometers matter, but the lateral extension of the cloud, which is tens of microns.
So it can be like an option to find that.
Yeah. That can be confining, localizing the excitation instead of exciting arbitrarily somewhere in between, putting atoms, confining even further, so maybe confining them into the lattice or pinning them with dipole traps. These are or very valid options.
Okay, so dipole trapping would be possible.
Yeah, they are possible. Yes, absolutely. Yeah, not yet implemented. Yeah.
Further questions? Don't see any at the moment. So let's